This is Unit 2, Topic B. We've been looking at how to algebraically or analytically calculate a derivative. And I now want to actually turn back to where we started, which was how do you look at a derivative in terms of a graph? We're going to look in this section at being given some graphs, and we're going to try to sketch a graph of the derivative function right on the same axes. Now, in order to do this, keep in mind the derivative is always the slope of the tangent line. So if I have a linear function like this, the slope of this line is the same everywhere, right? In fact, in this case, it looks like we've got a rise of 3 and a run of 1. So in fact, everywhere, the slope is just equal to 3. That means the derivative is equal to 3 all the time. And if I were to draw that derivative graph, it would simply have a value of 3 at all times. So the original given function was f of x, and the function I just drew here was f prime of x. In this case, always equal to 3. All right, the next graph is probably also a bit familiar. We worked with this one in the last section, right? It's just the y equals x squared graph. Let's think graphically for a moment. If you think about the slopes of the tangent lines, I often, when I look at a new graph, like to start by saying, gosh, is the tangent line going to be horizontal? Is the slope or derivative going to be 0 anywhere? And of course, in this case, yes. Right here at x equals 0, right at that minimum point or vertex, if you were to draw a tangent line, it would be perfectly horizontal, meaning right here, the slope is 0. To the left of that, all of the tangent lines would be downhill. They would all have negative slopes. So the slope is negative over here, and over here all of our slopes would be positives, right? All of the tangent lines would be uphill or having positive slopes. So when I go to draw my derivative, I would like to draw the graph of a function that's 0 right here, has negative values on this side and positive values on that side. Now this one we have an advantage. We actually already know the derivative function for y equals x squared. We calculated it. The derivative was 2x, right? So let's actually graph the line y equals 2x this time since we do know that. And just verify that it does what we expected it to do based on our graphical analysis. And indeed, right, it's negative on this side, negative values, positive values on this side, and 0 right there at the vertex. We're going to use the same kind of thought process to work with graphs of functions that we don't necessarily know the equations of, like we had the advantage of knowing here. So in the third example, right here, do you see any places where you'd have that horizontal tangent line, where the slope or derivative would be 0? And I'm going to say, yeah, right here, right? If you were to draw a tangent line, it would be horizontal. And right about here, that means the slope or derivative would be 0. It happens again here, just before x equals 3. We'd have a horizontal tangent with a slope or derivative of 0. So right around there. And again, I'm writing slopes, but remember, every time I'm thinking slope of the tangent line, I'm really thinking derivative. All right, to the left of where the slope is 0, all of my tangent lines would have positive slopes. So I'd have positive derivatives here. In this little section of the graph, between the two places with m equals 0, I would have negative slopes. Again, if you were to draw tangent lines, they would be downhill or negative slopes. And then over here, we're sloping upward again, so positive slopes. Now I'm not going to be able to be quite as accurate as I was last time, where I actually already knew the exact equation for the derivative, but I can draw a reasonable interpretation here. I'm going to start by saying m is 0 here, and again there. So let me plot those two places where my derivative function is exactly 0. And then I want to say positive derivatives over in this section. Now notice it's steepest at first, and it gets less steep as I approach this. So they're going to start out pretty big, and they're going to get smaller until I hit that 0. Negative derivatives in this section, none of them are particularly steep, so I'm just going to show some kind of small negative numbers here. And I have to come back up and hit that 0. And then over here, those positive derivatives just keep getting steeper and steeper again. So I'm going to say my f prime function is going to look something like that. And just to make sure that's really visible, I'll go over it, make it a little thicker for you. So that's my graph of f prime. All right, what about this fourth one? Looks like an absolute value graph, and it is. That's my f of x. And I'd like to start by talking about whether there's any place where the derivative is 0, any place where you see that you would have a horizontal tangent line. If you're looking at the vertex, I'm not surprised, you probably should be, but I claim right there the derivative is actually not 0. If I asked you to draw a tangent line right at x equals 0, what would you draw? Well, it would kind of depend on which way you were traveling. If you were coming from the left-hand side, the slope is -1 all the way down through here, right? And if you couldn't actually see what happened right at 0, you would just assume that the slope was going to continue to be -1 based on the pattern that's already been established. But if you started on this side and were traveling towards 0, you would be seeing a slope of +1 all the way through here, and you would assume again that it would continue to be +1. This is very much like the idea of a limit. When we come to a limit from the left side and we get a different value than we get when we come from the right-hand side, we say the limit doesn't exist, right? It's kind of confused, so to speak, right at x equals 0. So in this case, I'm going to say at x equals 0, the slope is undefined, doesn't exist. Right there at 0. And again, it's the same idea as the limit from the left and the limit from the right being different, making the limit not exist. On the left side, as we said, though, there's a constant slope of -1. And on the right-hand side, there's a constant slope of +1. So when I go to draw my derivative function, it's just the constant -1 over here and the constant +1 over there. Since the limit is undefined right at 0, I'm going to show open circles in my derivative graph at x equals 0 for both pieces. And there's the graph of f prime. All right, a few more on the next page. In this next graph, I don't actually see any places where the slope is 0, right? There's never a horizontal tangent on that graph. But there is kind of an interesting point. Look at what happens at -2, right there. If you had to draw a tangent line at -2, what would it look like? Well, coming in from the left, the slopes seem to be getting bigger and bigger and bigger, right? In fact, right at -2, it appears that the tangent line would become vertical. And in fact, it does. coming in from the right, we'd have positive slopes again and again. Those positive slopes are just going to get bigger and bigger and bigger as we approach the point at x equal 2, where really the only reasonable tangent line would have to be perfectly vertical. So I'm going to say, right here, slope is undefined again, but for a different reason this time. It actually gets infinitely steep. We can't give it a numerical value, but we do know that it goes toward infinity. That means that when I graph this derivative function, I would expect a vertical asymptote in the derivative function, allowing it to go to positive infinity on both sides. Now notice here, these are all positive slopes of tangent lines. And here still, positive slopes of tangent lines. So my derivative graph is going to be positive everywhere, with a vertical asymptote going off towards infinity, right here at -2. So let's see what we can do with that. I'm going to put in my vertical asymptote. And I know I have to go up towards positive infinity on both sides. These slopes out at the ends here are small, right? This is getting flatter and flatter, closer to 0, but not equal to 0. So I'm going to show my derivative function being close to positive infinity near that vertical asymptote, and then getting smaller and smaller. And it's actually going to approach a horizontal asymptote of 0 as these slopes get very, very small, right? Those would just be small fractions. The same thing's going to happen over here on the left. Again, these slopes stay positive, but the further away from that -2 I get, the flatter the graph gets, the closer the slope gets to 0. So I'd have a horizontal asymptote really on both sides, which we could make more official by drawing it in as a horizontal asymptote. Okay, next graph. Here's my f of x. I guess I didn't label this one. This, again, was f prime here, and the original one was f. Here's my graph of f of x this time. And I once again don't see any place where the graph is truly horizontal, although I will say it's very close to horizontal over here at the end behavior, right? We're approaching that horizontal asymptote. So I know that my derivative is going to be really close to 0 on the ends, kind of like it was over here. Right at x equals 0 this time, the function itself has a vertical asymptote. So the slope must be undefined. There is no y value there. So I certainly couldn't draw a tangent line at that point. On the left side, I can see that my tangent lines would all have positive slopes, right? Really small positive slopes over here, getting larger and larger and larger as I approach that vertical asymptote. So positive slopes here, tending toward infinity on this side and toward 0 on that side. What about over here? All of my slopes on this side, if I imagine a tangent line, would be negative. Again, over here, there are very small negative numbers, almost horizontal, so tending towards 0 out here. And getting steeper and steeper, but still a negative slope, so tending toward a slope of negative infinity near the asymptote. So let's draw our derivative function. It does indeed look like I would have that vertical asymptote at 0 again. So I'm just going to put that in as a guideline for myself. And since we're tending towards 0 with my end behavior, I think I'm going to have that horizontal asymptote at 0 again as well. All right. On this side, we've got our positive derivatives everywhere. So close to 0 out here, and then going up towards positive infinity near the vertical asymptote. So the graph of the function and the graph of the derivative are going to look very similar on that side. Over here, though, all the slopes are negative, tending toward negative infinity near the asymptote, and then coming up towards 0 for the end behavior. So there's my f prime in pink here. All right, we've got 2 more to look at. In this next graph, once again, I see no true horizontal asymptote, or excuse me, no true horizontal tangent lines. I do see a horizontal asymptote in my original function here, so my slopes are very close to 0 on this end. Sorry, first Saturday of the month, they're testing those sirens. There we go, getting quieter again. All right, so I know my slope will be close to 0 over here, although not quite equal to 0. It's asymptotic, right? Everywhere on this whole graph, the tangent lines would really have positive slopes, right? They always are sloping upward everywhere I look here. So my slope is positive everywhere. But they're going to be very small positive slopes on this side, so tending towards 0 on the left end, and very large positive slopes over here, getting bigger and bigger, so tending toward positive infinity on that end. If you think about this one, would you agree with me that what I just described for the slope is really what the original function looks like? Positive but very small on this end, positive and very large on that end. So if I were to draw the derivative function here, I think I would actually draw it almost identical to the original function. Very small but positive on the left end, continuing to very large and positive on the right end. So in this case, I'm saying that I think the derivative function is the same as the original function. Keep that one in mind. You probably recognize that graph. It's a specific type of graph that you studied a lot, right? We're going to come back and talk about it in another couple of sections. All right, our last graph. Doesn't really matter. Let's just put a solid dot and an open dot on that one. Probably should have done that. Clearly there's a jump discontinuity right here at x equal 1, meaning that the limit of the actual function doesn't exist, and therefore the derivative can't possibly exist either. So I'm going to say for sure here at 1, the slope is undefined. The slope coming in from the left and the slope coming in from the right are very different. Coming in from the left, I do have all positive slopes, right? Every tangent line here would have a positive slope, although they're getting closer and closer to 0 as I approach that hole in the graph. So positive values getting closer to 0. And on the right-hand side of that undefined slope, this is just a straight line. The slope is -1 all the way through here. All right, so let's see what we can draw. To the right of 1, the slope is always -1. That's easy. Since slope is undefined right at -1, I'll have to put an open circle there. And then over here on the left-hand side, positive values that started out bigger, but were getting smaller and smaller, closer and closer to 0. So I'll just have a large positive slope getting really close to 0. Oops. I didn't do that very well. Getting really close to 0, but I should have been getting close to 0 there. Ignore that line I just drew. I'm going to get rid of it. I actually have to get close to 0 here. And then the slopes just get bigger and bigger as I move away from there. That should not be there. And there we go. There's the graph of our derivative function. All right, that brings us to the end of section 2b. Again, you're not expected to find any numerical values here, no algebraic values. You're just using the graphs themselves to determine the slopes, to determine the derivatives.